And it shouldn't be clear yet at all. So I'm going to hopefully tell you why. Let's get those names here in a minute. But first, let's see some examples to hammer home what I'm talking about here. Let's make this definition precise with some examples. Okay. So I'm going to give you an example of something that is regular, and then I'm going to give you an example of something that's not regular. So hopefully we can see clearly what the difference is, what makes something regular. So here's something that is regular. First example. Suppose my Markov chain has this transition matrix. 1 half, 1 half, 1, 0. Okay. So this is a transition matrix for Markov chain, and I claim it will be regular. Why? Well, let's just take the square of this thing. Let's just take the square of this. What do I get? Well, I'm going to get 1/4 plus a half. That's 3/4. I'm going to get, let's see, 1/4 plus 0, a half plus 0, and a half plus 0. So if you square this matrix, and again, I invite you guys to work that out more carefully than what I did at the board here. But when I square this matrix, I get this. And look at every entry of this matrix. Everything is bigger than 0. These are all positive numbers in my matrix. So every entry is a positive number. So this is a regular Markov chain. Because every entry of p squared is positive. None of them are 0. So there we go. So k is 2. If k from my definition that I wrote a minute ago is 2 in this example. I only had to find the second power to get a matrix that had all non-zero entries. But that's enough for this to be regular. So it doesn't matter what k is. There might be examples where you have to take the third power or the fourth power or something crazy, the 1000th power, I don't know. It doesn't matter. As long as there's some power where you get everything as positive, you're good. It's regular. This sort of raises a question, which is, how do you know if it's not regular? Maybe I take the second power of something, and there's a 0 that pops up, and so it's not. I don't know if it's, I can't say it's regular yet. But it just has to work for some power. So maybe some really big power it works, like the millionth power or something. How do I rule that out? And my answer is that maybe in general you can't. So maybe sometimes it's really hard to tell if something is not regular. But maybe there are certain examples where we can tell. And so here's an example where I claim we'll be able to tell that it is not regular because of a very special property that'll happen. So let's have another Markov chain with this transition matrix. Oops. That's what I want. So here's this transition matrix, 0, 1, 1, 0. So we just asked the question, is this regular? Is this regular? I don't know. Well, I guess I do know, but you guys don't know. Or maybe you do. Anyway, let's find out for sure whether or not this thing's regular. So what do? Well, I just start taking powers of it because I know that the definition of regularity calls for taking powers of this and looking at the entries. So let's just start taking powers and see what happens. So what's p squared? P squared is, well, I just take this row times first column is 0, 1, so 1. 0 times 1 plus 1 times 0, that's 0. 1 times 0 plus 0 times 1 is 0. And 1 times 1 plus 0, that's just 1. So here is p squared. It's the identity matrix, the 2x2 identity matrix. Good. It's still a transition matrix. The rows add up to 1. But as you'll notice, I have entries that are 0. So I can't conclude that this is regular because I took a power of it, but I still have zeros. So far, it's not looking regular, but I can't conclude that yet because I've only checked one power, right? So I basically have gotten nowhere yet, but that's okay. The next thing to do then would be, well, let's take the third power. Let's take the next power and see what happens. Maybe this will tell me whether or not it's regular. Okay, what's the third power? Well, to find the third power, I could multiply this by itself 3 times, or I could recognize that p cubed, p to the third power is the same thing as p times p squared because exponents add. So I could take p times p squared instead. So I could take this times this. What is that? Well, as I said a moment ago, this is the identity matrix. And you guys know about the identity matrix. Multiplying by it doesn't do anything. So when I take this times the identity matrix, I just get this. I just get back to this. So I'm not even going to write it as a matrix. I'm just going to straight up say p to the third power is just p. I get back to where I started from when I get to the third power. So this is like on a cycle, it looks like. When I get to the third power, I get back to where I started. And then as I take a further power, I'm just going to get back to this. And it's going to just flip-flop, and it's just going to flip back and forth between these two matrices as I go. So, p cubed is p. That means that p to the fourth power is actually just p squared, which is the identity matrix. And then p to the fifth power means that I'm going to get back to p and so forth forever. So what do we see? I see that the sequence of powers, p squared, p cubed, p to the fourth, p fifth, p sixth, p seventh, and onward forever is just going to alternate between the identity and p. As I take powers, it's just going to flip-flop between these two matrices. I'll never get anything different as I take powers. So what does that mean? Well, notice both of these matrices have zeros in them, which means no matter what power I take, I'm always going to have an entry that's 0. I'll never get a matrix whose entries are all not 0. So in this particular case, I can conclude that no, it is not regular. This is not regular because I know what all of the powers of the matrix look like for all time, for as big of a power as I want. It's one of these two matrices, and they both have zeros, so it cannot be regular. Okay. So this is a very special example where I have this sort of cyclic thing going on. It just flip-flops, goes on a cycle between these two matrices. So if you're ever in a situation like this where it cycles back to the identity matrix after so many powers, then you can basically conclude that it's not regular because that identity matrix has zeros. So you're toast. It cannot be a regular thing. So that's a very special class of things that are definitely not regular. Not the only things, but one class of such things that you may encounter in a homework problem or something. So anyway, here we go. That's something that's not regular. So if you want more examples of things that are regular, we'll have more in class. But actually, we already had a couple earlier in class. That weather example, for example, was a regular Markov chain because, that initial transition matrix had non-zero entries to begin with. So it was already regular from that. And the second example we did was also regular because its square had all non-zero entries. So look back at those examples for some more examples of regular Markov chains. Okay, check the clock. 20 minutes. Cool. I don't know if I want to talk the entire time. So probably what I'm going to do now is I'm going to introduce sort of the big idea of where this is going with this idea of stability. And then I might mention a word about how we're going to solve a certain problem, but I probably will go into detail about that tomorrow as far as actually solving. So I think today I'm going to finish off just by motivating or telling you basically where this is all going. And then tomorrow, we'll start solving stuff. I'll show you how to get down and solve a certain problem that we're going to introduce here. So we need to talk about stable probabilities. So this is what I was getting at before. Regular Markov chains have stability in a certain sense. And I'm going to tell you what that really means now, mathematically. What do I mean by stability? And so here's how this goes. If P is regular, so if I have a regular Markov chain, then the following thing is true. There is a unique probability vector and your book calls this W. I don't know where W comes from, but that's what I'm going to use also to be consistent with your book. So I have a Markov chain with n states. If it's regular, I'm saying that there is a unique probability vector W with n entries, so that the following thing is true. So it has the following property. For each state J, the probability of going from state I to state J after k steps, or k transitions, is arbitrary, so let me just write this sentence and then I'm gonna have to explain what it means, is arbitrarily close to Wj for large K. Okay. If you have any exposure to calculus whatsoever, this kind of phrase is very common. But if you don't, then it probably feels a little weird, and that's okay. This is not a calculus class, so I'm not going to talk about things like limits. Instead, I'm going to write this on the board, and then I'm going to explain what it means a little more intuitively. So what am I saying here? There's some special vector out here, some special probability vector that has some numbers in it. And what I'm saying here is that if I do enough steps, so when I say for large K, I just say do a ton of steps. If I do enough steps in my Markov chain, then the probability of going from some state to another, so from some state to another state after that many steps is basically just the number Wj from my vector. So in a sense, this vector just contains all of the probabilities of going from one state to another after a large number of steps. So after a very long time has passed, potentially. So in some sense, over enough time, all the states are sort of tending to, the probabilities of being in a given state is just tending to the numbers inside of this vector. Everything's moving towards this vector over a long time. Maybe I could put it this way, you know, xk is x0 times p to the k. So maybe what I could say is, as k is getting really big, as I take bigger and bigger powers, this vector is getting closer and closer to looking like this vector. It's another way to say this. Okay. Okay, so this is true, what's written on the board, and it's interesting that this happens. But in practice, it's not necessarily the easiest way to think about things, especially in this class where we don't talk about calculus. So it's not, you know, it's interesting that things like tend towards some fixed vector like this, some special vector sort of captures the long-term behavior of the Markov chain. That's interesting, but it's not very